All right, well, after looking at the textbook, it doesn't say anything about the fact that I just changed this one and now it doesn't meet the third criteria. And I changed this one, it doesn't meet the first criteria. But I don't know. I don't understand it. But we're going to move on because based on what we have here, we can still say this is removable. It's just there's nothing you can do about it to become continuous, which is what I thought the whole point was, but apparently it's not. So we're just labeling them for labeling them's sake. All right, so g of x equals 1 over x. If you think about this function, the denominator can never equal 0. So what we have there, if you think about the graph, is it's actually a rational function. You could graph that on the graphing calculator and you would see a vertical asymptote at x equals 0. So what this means is that the first condition is not met. So there's a discontinuity there. But now we have to determine, is it removable or not? So is there any way that we can redefine this so that f of c exists? Because right now it doesn't. Well, according to this book, you can't, because even if you defined f of 0, so you gave it a value at x equals 0, and so you plopped a point like right here, it still wouldn't make a difference because it still fails to have a limit. So it still doesn't meet the second condition, which is that the limit exists. So there's nothing you can do about it because it fails condition 2. All right, so for the next one, again, we have a denominator, and that means that x cannot equal 1. So the same thing is going to kind of occur here. If we grab a graphing calculator, and we look at this graph, and we got x squared minus 1, oh, I gotta put that in parentheses, divided by x minus 1, and we graphed it, that would create a line, except there would be a hole here at x equals 1. So what we could do is we could actually, on this one, since there's no asymptote, let's just draw a little graph over here really quick. It's something like that. What we can actually do is we can redefine this one. We can say that h of x equals x squared minus 1 over x minus 1 for all values except x cannot equal 1. Okay, but then we're going to say that this function equals 1 at x equals 1. So we're going to have a point and we're going to fill it in right there. I guess that's how you can redefine them. So like my little meltdown I was having about these over here, I should have actually put the point in the open circle, I think is what I was supposed to be doing. I was supposed to be putting them in there. So I'm going to fix this. There we go. All is right with the world now. Okay, so we've just redefined it. Oh, crud. I don't know if you saw what I did. Here you go. You see what I did now. So I redefined it so that now that even the third condition is met, because the limit and f of c are both equal. Okay, so back to this. We've redefined it so that all three conditions are met. F of c exists. The limit of f of x as x approaches 1 exists. And the limit and the function are both the same value because we filled in that hole. So yay, this one was fixable. So you can call this one non-removable and this one removable. And I'm sorry, you guys, if you're completely lost, please, let's just flesh this out tomorrow. But I feel like this was a good groundwork for us to work from.